Welcome to MOVIMOT and Field Distributors Basic and Intermediate Training. This is session 11, which happens to be the final session of this class. We're going to wrap up this class by learning about fieldbus communication so you can understand how you can communicate between a PLC or other industrial controller and the fieldbus interface on a field distributor that's controlling a MOVIMOT. Let me open this topic by giving you a very important note. While each fieldbus standard is different, in other words, Profibus, Profinet, Ethernet IP, DeviceNet, what you do to control the MOVIMOT is the same. So in other words, even though the fieldbuses are all different, what travels over the fieldbus, the MOVIMOT control protocol, is the same. It's fieldbus independent. That's a very powerful idea, because if I had to teach you how to control each individual fieldbus interface in a different way, we'd be here all day, because there are quite a few of them. Happily, that's not the case. We just have to learn one protocol, and we're good to go. Before we talk about the protocol, though, I would like to just kind of outline how fieldbus control works, and this is the same regardless of the particular brand of fieldbus. A fieldbus will have one or more VFDs attached to it. In this case, we have MOVIMOTs with field distributors. There will be some kind of control device. In this case, I have a Siemens PLC. The fieldbus connects everything together and provides communications. The devices on the fieldbus communicate by exchanging what are called process data words, or PDs. Process data words come in two types: process output words and process input words. Which one is which? Well, a helpful thing to remember is that everything is labeled from the perspective of the PLC. So in other words, process output words, which are abbreviated PO, go from the PLC to the VFD. In other words, the PLC outputs them. Process input words, abbreviated PI, go to the PLC from the VFDs. So the PLC inputs the information from the fieldbus. Let's say our PLC is trying to control the Z8 field distributor, which is the one on the far right. What it would do is it would transmit process output words onto the fieldbus. The field distributor would intercept them and control the MOVIMOT, and then it would send process input words back to the PLC, which would provide things like status information. That's the general picture of how fieldbus communication works and the kind of things that you'll see on a fieldbus. Let's talk in a little more detail about process data words. This is really the key to understanding the protocol by which a PLC can control a MOVIMOT over a fieldbus. All process data words are 16-bit binary numbers. So they look something like this. They have 16 bits. The bits are numbered 0 through 15. The least significant bit is on the right, and it's bit 0. The most significant bit is bit 15. It's on the left. Now, broadly speaking, process data words can perform one of two functions. The first category of function is bits with individual significance. In other words, the individual bits within the process data words behave sort of like switches or status indicators. They turn on and off individually to either control something or reflect something's status. Typically, when you're communicating with the device, at least one process data word will be what's called the control word. That word will have bits that are flipped on and off individually to activate or deactivate different functions. Usually, there will be one or more process input words that will provide status information, and those bits will turn on and off to reflect the status of various things within the VFD. So that's the first function that a process data word can perform. The second one is simpler. The bits all just form a single number in binary, and that represents some kind of value. For example, a parameter or a status word that provides information like how fast the VFD is turning the motor. So let's look at some examples. Let's look at the first type where the bits have individual significance. And I'm going to stress these are generic examples. This is not how the MOVIMOT works. This is just an illustration of how this kind of process data word could function. We'll look at a PO first. In this category of process data word, the individual bits perform control operations. So for example, maybe these bits are labeled and they perform specific functions. Bit 0 is inhibit, so that might inhibit the controller. Another bit might enable it. 2 bits might control the direction of rotation clockwise and counterclockwise, and 1 bit might trigger an emergency stop. So those bits, the ones or zeros, are going to trigger those actions. The red bits are the control bits. The black bits are what we call don't care bits. Usually you just set them to 0. They're ignored. So in this case, only 5 bits have any specific meaning. In a process input word, it's the same general idea, except instead of controlling something, they're providing status information. Maybe we have a ready bit, a stop bit, a break bit, and a fault bit. And these will tell us what's going on based on whether they're 1 or 0. So we have the red bits, which matter, and again, we have some black don't care bits. That's our first class of process data words. Now, in our second type of process data word, the word forms a binary number. In the case of a process output word, maybe it indicates something like speed, the speed that you want to run the VFD. So you send a number in binary format over the field bus, the VFD interprets that and runs at a particular speed, say 1000 RPM. Process input words can provide numeric status information. For example, maybe this process input word is sending back the amount of current the motor's drawing, the actual current, and maybe it does it as a percentage. Perhaps this number indicates that the VFD is drawing 56.3% of its nominal current rating. So this is an example of the second category of process data words, providing numeric information. I should mention here at this point that the numeric range of a process input or output word is minus 32,768 to positive 32,767. That's the numeric limit of what you can represent with 16 bits. A helpful tip: in most cases, when you're programming a PLC, process data words are usually expressed as 4-digit hexadecimal numbers, not binary, not decimal. You may be wondering, what is hexadecimal? It's an alternative number base that programmers use quite a bit. It's called base 16 because it has 16 symbols possible instead of the usual 10 that we're accustomed to in the decimal system. In decimal, we have the digits 0 through 9. In hexadecimal, you have the digits 0 through 9, plus you have 6 additional symbols, the letters A, B, C, D, E, and F. So if you see a number containing letters, it's probably hexadecimal. Binary numbers are used as well, but they're kind of cumbersome to work with because you have all those long strings of zeros and ones. So programmers tend to like hexadecimal better because you can convert back and forth between it and binary very easily. Incidentally, on this example here, you may be wondering what the 0x is. That has nothing to do with the number itself. It's simply a prefix that clues you in that it's a hexadecimal number. If you see 0x and then 4 digits, that indicates it's a hexadecimal number. If you see 0b, it indicates it's a binary number. Of course, binary numbers are very easy to spot because they're just zeros and ones. Now, you're probably thinking, if you're not a programmer, whoa, how do I deal with hexadecimal numbers? I've never worked with them before. Well, there's a very simple solution right at hand. You can use the calculator built into Windows. The Windows calculator has a programmer mode, and if you click the menu on the left side, you can change from the standard calculator to a programmer calculator, which will convert back and forth between hexadecimal, binary, and decimal. Now, how do you use this? Well, let me give you a few pointers here. You want to click where the arrow is until it changes to word. It will probably start out as Q word, and if you click it once, it'll change to D word, and if you click it one more time, it will change to word. When you put it into this mode, it will limit the results to 16 bits, which is the length of a process data word, so that's a handy thing to do. And if you want to make a number negative, you'll need to click the positive-negative button. Don't hit negative on the keyboard. The Windows calculator is very helpful when you have to represent negative numbers in hexadecimal because the process of converting a number to a negative form by hand is a little cumbersome. So to use the calculator, it's really simple. You enter the decimal value. If necessary, hit the plus-minus key, and then simply look over where it says hex, and you will see the conversion in hexadecimal format. By the way, you always want hexadecimal numbers to have 4 digits to them, so if they have fewer than 4, just add zeros to the left side to pad them out. In this case, 3E8, you would write out as 03E8. and that would be the correct length for a process data word. Really simple. Okay, so that takes care of some of the preliminaries. Now we're ready to move on to the MOVIMOT and Field Distributor Communications Protocol. We'll learn to control a MOVIMOT through its field distributor by sending an appropriate protocol over the field bus. I'd like to mention something very important here. This is crucial you understand this. The way you set up and program field bus communications is going to vary with each PLC brand and its software. So if you're using a Siemens PLC or an Allen Bradley PLC or some other brand, obviously there are going to be differences because they all have their own software, they all have their own preferred programming scheme, so there are differences. We're not going to get into that here. Instead, what we're going to do is focus just on the protocol that you send over the field bus to control the MOVIMOT. We're not going to get into specific PLC level details. Again, we'd be here all day if we had to do that. However, if you go to the manuals that go with the field bus interfaces, they give specific details for specific brands of PLCs. What's really important, though, is that you understand the protocol, and that's what I am going to cover here. The protocol we're going to use is called 5PD. This is one of several possible protocols that you can use to control a MOVIMOT. We're not going to cover the others. 5PD is the most popular and the most powerful, so that's the one we're going to learn here. Here's the general idea. The PLC and the field distributor are going to exchange 5 process data words in each direction. And here they are. These are the process output words that go from the PLC to the MOVIMOT, and these are the process input words that come back from the MOVIMOT to the PLC. The MOVIMOT uses 3 of these PDs, and the field bus interface uses 2. So these 3, PO1, PO2, and PO3, control the MOVIMOT. PI1, PI2, and PI3 reflect its status. Let me tell you what each one of these does. Process output word 1 controls the VFD. By flipping individual bits in this word, you can tell it how to operate. PO2 provides the speed, telling it at what speed to turn. PO3 contains the ramp value, telling it how to accelerate or decelerate. PI1 provides status information telling you what's going on with the VFD. PI2 is customizable. It can send back one of several pieces of information. I'll show you how to pick which one in just a minute. PI3 is a second status word that provides some additional information about the VFD. Now, the other 2 PDs reflect information about the field distributor itself. PO4 is used to control the digital outputs on the field bus interface. Remember, the field bus interface may have some extra I/O. If there are digital outputs, then sending information in PO4 will allow you to turn those on or off. PI4 and PI5 provide information about the field bus interface. PI4 gives you the status of its digital inputs, if it has any, and PI5 is another status word that gives you information about what's going on with the field bus interface. We won't really talk about those a lot. You can look those up in the manual if you're curious. We're going to focus on the 3 process data words that control the MOVIMOT, PO1, 2, and 3, PI1, 2, and 3. Now, I mentioned that process output word 2 and process input word 2 are customizable. So let's talk about how you customize them. You do this by going to the MOVIMOT's parameter tree. You go to parameter group 8 and subgroup 7, and you will be able to customize PO2 and PI2. PO2 is always going to control the speed, but you have 2 ways to send the speed. You can either send it in RPM, that's set point speed, or you can send it as a percentage, set point speed percentage. That will be a percentage of the maximum speed that you've either dialed in with the F1 dial on top of the control head or that you've set by a parameter. By default, the MOVIMOT will look for a percentage, but you can change this to RPM if you wish. PI2 can report either the motor's current speed or the amount of current that the motor is drawing. If you pick actual speed, you'll get a speed value in RPM. If you pick actual speed percentage, you will get that as a percentage of the motor's maximum speed. Active current will give you the actual current the motor's drawing, and output current will tell you the apparent current that it's drawing. So these are the choices available to you. You can pick any of these. And by the way, after you change one of these, parameter 876 will probably change to no. you need to change it back to yes so that the MOVIMOT will respond to POs coming to it from the field bus. If this value is set to no, then the MOVIMOT will not respond to commands. All right, let's talk about the three POs. We'll talk about PO1 first. That's the control word. It has 5 bits in it that control how the MOVIMOT behaves. All the other bits are don't cares, so the bits in red are the important ones. The first 3 bits, 0 through 2, tell the MOVIMOT to either run or stop. If you send a 110, it will run, and if you send a 010, it will stop. So very simple there. Bit 6 is for resetting faults. If your MOVIMOT has faulted, you can reset it by switching this bit to 1 and then changing it back to 0, and that will clear the fault. And bit 8 allows you to manually release the brake if you have enabled that function either through the dip switch or an appropriate parameter. This allows you to release the brake without enabling the drive. We talked about this in an earlier session. You can do it over the field bus through bit 8. So just by example here, if you want to run the MOVIMOT, then send this binary pattern, which translates to hexadecimal 0006. Pretty simple. The speed word is a little more complicated because, as you just learned, you can send the speed either as a percentage or as RPMs. I'm going to show you how to encode both of these. Let's say you want to send the speed as a percentage of the motor's maximum speed. You'll have to do some calculations first. So here's what you do. You take the speed that you want to turn, divide it by the motor's maximum program speed, and multiply by 100%. That will give you the speed as a percentage. Then you must take that value and divide it by 0.0061%. That is the smallest unit that you can turn. And that will give you a number that, after you've converted it to hexadecimal, you can send it over the field bus. To turn clockwise, provide a positive hexadecimal value. To turn counterclockwise, send a negative hexadecimal value. So let me give you an example to show how this would work. Let's say that you want to turn at 1170 RPM when the motor's maximum program speed is 1800 RPM. First of all, you'll calculate the speed as a percentage. Take 1170 divided by 1800 times 100%. And you need to turn at 65%. Then take 65% divided by 0.0061%, and that gives you 10,656. You'll then need to convert this to hexadecimal. If you want to turn clockwise, you will send the hexadecimal value 29A0, and if you want to turn counterclockwise, you'll have to convert this to the negative hexadecimal value of D660. I recommend you use the Windows calculator for this, since converting signed hexadecimal numbers by hand is a little cumbersome. So that is how you would control the MOVIMOT sending speed as a percentage. Now, what if you wanted to just send simple RPMs? That's a little easier. Here's what you would do. If you want to express the speed directly as RPMs, you would take the speed you wish to turn, divide by 0.2 RPM, and that would give you a number that you could convert to hexadecimal. Again, positive numbers will turn clockwise, negative numbers will turn counterclockwise. So another example here, let's say you wish to run at 955 RPM. What you would do is you would take 955 RPM and divide by 0.2. That would give you a speed value of 4,775. You would then convert that to hexadecimal. The clockwise version would be 12A7. The counterclockwise or negative version would be ED59, and that is what you would send in PO2. So your choice, it just depends how you have PO2 configured. All right, PO3 is the ramp word. This is where you control the MOVIMOT's acceleration and deceleration. This is similar to what you did before when you programmed the ramp by the T1 dial. You had to calculate the ramp time. You pretty much do the same thing here. There's just one difference. Ramps are expressed in milliseconds. That's 1/1000th of a second rather than seconds. That gives you the ability to express ramps in very fine time units. So you would take our old familiar formula, you would calculate the ramp time and then multiply it by 1,000 to get your ramp time in milliseconds. Let me give you an example here. Let's say we have a 4-pole motor. We want to do a 500 RPM speed change. In other words, go from 0 to 500 RPM. And we want to do that in 2 seconds. we would plug it into the formula. We'd take 2 seconds times 6,000 divided by 500 RPM times 4 poles. That would give us a time of 6 seconds. Multiply that by 1,000, and that's 6,000 milliseconds. Then we convert that number to hexadecimal, and it is 1770. And that would give us a ramp time of 2 seconds for a 500 RPM speed change. Pretty simple. All right, let's talk about the words that come back from the VFD to the PLC. PI1 is a status word. It has a number of bits that are significant, the ones in red. The black bits are don't cares. They will typically be 0. You should just ignore them. If a bit is 0, it means it's either false or something isn't enabled, and if it's 1, it's true or it is enabled. So for example, output stage enabled. If you see a 1 in bit 0, that means that the VFD has turned on its transistors and probably it's getting ready to run. Bit 1 indicates if the inverter's ready or if it's not. If it's 1, it means it's true, the inverter is ready to go. If it's 0, it's false, it's not ready to go. Bit 2 simply indicates the VFD is listening for PO data from the PLC. If it's 0, it means the VFD is going to be ignoring this information and it won't respond to commands. Bit 5 indicates if the VFD has faulted or not. If it's a 0, the VFD is fine. If it is 1, then there's a fault. If you want to find out what the fault is, or you want to find out simply the status if the VFD is not faulted, you look at the last 8 bits, and these together form a binary number which indicates the fault or the status code. To get the numbers, of course, I refer you to the MOVIMOT manual. So that's PI1. PI2 is a customizable word. It's going to either reflect the amount of current the motor's drawing or the speed at which it is turning. By default, it expresses current, and that is a percentage. And to interpret this, you convert it from hexadecimal back to decimal, and you put a decimal point between the last 2 digits. There is a single imaginary decimal point there. So for example, if you get 01B5 coming back in this word, what you would do is convert it to decimal, which is 437, and you would insert a decimal point between the last 2 digits, and that would be 43.7% of I sub n. So that's how you would interpret this if it's reflecting current. On the other hand, if it's reflecting speed, you would interpret it either as RPM or a percentage of the maximum speed. You would need to know which one it's set to so you could interpret it correctly. You would simply convert it from hexadecimal to decimal, and if it's in RPM mode, multiply by 0.2, or if it's in percentage, multiply by 0.0061. So for example, let's say we're in percentage mode and you get a 3555 coming back. First thing you do is convert it to decimal. That's 13,653. And then you would multiply that by 0.0061, and that would give you 83.3, and that is a percentage of the maximum speed. Fairly simple, but definitely you have to do a little math here. Process input word 3 is another status word. It is similar to process input word 1. In fact, a lot of the information is a duplicate of what's in PI1, but there are some differences. Of course, again, if a bit is 0, it's false or indicates something isn't enabled. If it's 1, it indicates something is true or it is enabled. Now, bits 0, 1, 2, and 5 are identical to the corresponding bits in PI1. This is just duplicated information. However, bit 8 is different. It indicates if the brake is engaged or disengaged. If it's a 1, the brake is engaged. If it's not, it's disengaged. Bit 9 is a duplicate of bit 1. It indicates if the inverter's ready. The next 3 bits reflect the status of the MOVIMOT's digital inputs. That's F1, F2, counterclockwise and clockwise. And the final bit here, bit 13, indicates if the MOVIMOT is in expert or easy mode. If it's 1, it's in expert mode. If it's 0, it's in easy mode. I'm not sure why you really want to know that over the field bus, but it is available if you should for some reason. All right, so that is the protocol by which you will communicate with the MOVIMOT over the field bus. Now, how are we going to do this? We're going to do a hands-on shortly where we control our MOVIMOT over the field bus. We're going to use a free tool that SEW makes available. It is called the Ethernet Master Simulator. And this is just a handy little utility which allows you to simulate the operation of a PLC. Let's talk about it. We'll summarize the Ethernet Master Simulator's key features. It simulates a PLC communicating over a field bus, so if you're not a PLC programmer, you can still test your MOVIMOT just by firing this up on your PC, sending a few POs over the field bus, and you can confirm that the MOVIMOT is working correctly. And then once you're satisfied everything's working, you could hand off to a PLC programmer who would then take over and program the appropriate PLC using the appropriate software. So this is really just a testing and diagnostics program. It works either with Ethernet IP or Modbus TCP field buses, so you can use it only with those two. This does not work with Profinet or any of the older classic field buses. So if you have a different field bus, then you'll have to get a diagnostic tool elsewhere. But this one is good for these two, and these are very popular field bus standards. So it just sends POs to the device, and it monitors the PIs coming back from the device. Very simple. You'll be able to learn this in just 5 minutes. Where can you get it? You can go to scweurodrive.com, and I've included a link in the description below so you can download it and install it on your PC. Now, in order for the Ethernet Master Simulator to be able to communicate over the field bus, you're going to need to change your computer's Ethernet adapter to use a fixed IP address. In general, the Ethernet port on most computers will be set to automatically get an IP address from a Domain Host Control Protocol server, a DHCP server. What you'll need to do is disable this functionality and key in a static IP address. Now, how you do this depends on which version of Windows you're running. I'm going to show you an example on my computer, which is based on Windows 10. But if you're using Windows 11, it's going to be different. So you'll need to kind of take what I show you and figure out how to do the equivalent in the version of Windows that you have. So what you'll need to do is locate and open your network adapter and then change the IP version 4 settings to fixed values instead of DHCP assigned ones. For example, on my computer, the Ethernet port is called Ethernet 2. I would activate that. Then I would pick Properties. This screen would appear. I would find Internet Protocol version 4, which is right here. I would again click Properties. That would open up another screen like this. And then I would need to change the radio button from Obtain an IP address automatically to use the following IP address. I would then key in an appropriate IP address, subnet mask, and default gateway, and finally click OK. You notice in this case I have 192.168.10.200. That would certainly be compatible with the SCW Eurodrive default IP address that most of its products will be on, 192.168.10.4. Now, once you've done that, you'll have to do one final thing. You're going to need to register the Ethernet Master Simulator with the Windows firewall, assuming it is turned on. If you have a different firewall, then you'll probably have to register it with that program. Otherwise, it will get blocked and it won't be able to communicate with the field bus. So here's what you do with the Windows firewall. You open the Windows Firewall and Network Protection app, and you can use the Windows search tool, that's the magnifying glass, to find it. And then you'll need to add an app to its whitelist so the firewall will allow it through. So you'll add the Ethernet Master Simulator program to the whitelist. So this is kind of what it looks like. You would open up the Firewall and Network Protection app. You would then pick Allow an app through the firewall. This screen would appear. You would click Change Settings and then click the button Allow another app. This screen would appear. You would click the Browse button. Locate the Ethernet Master Simulator on your computer. It's called Ethernet Master Sim.exe. Click the Add button. This screen will appear. You'll need to do just one final thing. Find Ethernet Master Sim.exe and make sure that domain and public are both checked. And then click OK. And that will register the Ethernet Master Simulator with the firewall, and it should allow it to run without further problems. At that point, you can start up the Ethernet Master Simulator. Now, the first thing you'll need to do is you'll need to key in the IP address of the device you're trying to communicate with. In our last session, we set our fieldbus interface to the IP address of 192.168.10.100. So I put that in here. That's the IP address you're trying to reach. You'll need to change the protocol to Ethernet IP. You'll need to set both the process data exchange words to 5 because we're doing 5PD communication. You'll need to set the RPI timeout to 500 milliseconds, and then finally, click Open Session. And if everything is connected correctly, you should see this screen, meaning that you're communicating with the fieldbus interface. You'll need to do 2 more things, and then you'll be all set to go. You'll need to change the assembly instances to 150 and 140. That just tells it how to communicate with this particular device, and then finally click the Start button to begin the session. This screen will appear and you're good to go. You'll be able to enter POs in the first column and you'll be able to see PIs coming back in the second. I recommend that you uncheck the Auto Update PO box. If you don't do this, the minute you type a PO, it will get sent over the field bus. What I prefer to do is set up all my POs first and then click the Update PO button. So uncheck the box, edit the POs as required, click Update PO to transmit the POs, and you'll see the PIs come back automatically in the second column. And that is really all you have to do to use the Ethernet Master Simulator. It is a very simple program. So I think it's time to stop talking and have a hands-on. In our last session, we configured our MOVIMOT to work with the field distributor. We have to do a few additional tasks, and then we'll be able to communicate over the field bus. Here's what I'd like you to do. First of all, I'd like you to configure your MOVIMOT so PO2 accepts the speed in RPM rather than percentage, and PI2 reports the current speed in RPM. You'll need to go in and change 2 parameters to do that. Then you'll need to work out the PO1 values to run and stop the MOVIMOT. You'll need to work out the PO2 values for running the drive both clockwise and counterclockwise at 835 RPM. You'll need to work out the PO3 values for a ramp up time of 5 seconds and a ramp down time of 2 seconds for an 835 RPM speed change. Once you've done that, you'll need to set up the Ethernet Master Simulator on your computer, set up a fixed IP address, register with the firewall, and get ready to communicate. You'll need to get everything plugged in, and then you'll need to run the drive using the Ethernet Master Simulator, both clockwise and counterclockwise at 835 RPM with the calculated up ramp, in other words, the 5-second ramp. Finally, you'll need to confirm that you can stop the drive using the calculated down ramp, the 2-second ramp. So, pause the video and do the hands-on. All right, well, I hope that went well for you and that you were able to control your MOVIMOT using the Ethernet Master Simulator. I'm about to demonstrate this on my computer, but we need to do a little calculating first to work out some of those POs. We need to work out PO1. We need to work out how to run and stop the MOVIMOT. Now, run was easy. I gave that to you already. You just set the bottom 3 bits to 110, which translates to hexadecimal 0006. To stop the MOVIMOT, you need to send a 010 in the bottom 3 bits. That is hexadecimal 0002. So those are the 2 numbers you'll need to send in PO1 in order to run or stop the MOVIMOT. All right, we now need to work out PO2, which is our speed word. This tells our MOVIMOT how fast to rotate. We're supposed to turn at 835 RPM, both clockwise and counterclockwise. Since we're in RPM mode, what we're going to do is simply take 835, divide by 0.2. That gives us the number 4,175. We're going to convert this to hexadecimal. So if we convert positive 4,175, that is hexadecimal 104F. That's clockwise. And then negative 4,175 is hexadecimal EFB1. So if we send one of these values in PO2, we should get the desired speed and direction of rotation. We must calculate PO3 for our 2 ramps, 5-second and 2-second. Both of them have an 835 RPM speed change, so we just take our formula here and plug these numbers in. For the 5-second ramp, we take 5 seconds times 6,000 divided by 835 RPM times 4 poles. If you have a motor that has a different number of poles, you'll need to change that, but my motor has 4. And that gets us an answer of 9 seconds, which is equal to 9,000 milliseconds. Our 2-second ramp, same calculation with just one number different, gives us an answer of 3.6 seconds or 3,600 milliseconds. So we convert those two numbers to hexadecimal now. 9,000 in hexadecimal is 2328, and 3,600 is 0E10. And that gives us PO3, our acceleration and deceleration values. So let's go ahead now, get our MOVIMOT configured, fire up the Ethernet Master Simulator, and test everything out. All right, well, we're almost ready to control our MOVIMOT over the field bus, but we do need to do one thing first. We need to assign PO2 and PI2 so that they will accept and reflect the correct pieces of information. To do this, we go to parameter group 8 and expand it. We pick subgroup 7, process data assignment. We have two pull downs here, so we're going to change PO2 to set point speed, so it will accept RPM instead of percentage. And we're going to change parameter 874 from active current to actual speed, and that will give us our speed back in RPM. That's all we really have to do. We're all set to go now. However, we do need to do one thing, which I didn't mention last time when I was setting up my MOVIMOT. Remember, we're supposed to jumper our control head so that the clockwise and counterclockwise digital inputs are both connected to 24 volts. If we don't do that, then the MOVIMOT is not going to be able to rotate in both directions when we command it to do that from the field bus. Now, in my case, since I have a demo unit, I have switches connected up to the digital inputs, so I'm not going to take the control head off and install jumpers. I'm just going to turn on the two switches associated with clockwise and counterclockwise to simulate putting jumpers in the control head. That's a little more convenient. So let's do that now. Let's turn those two switches on, and that should take care of it. Now, I've connected an Ethernet cable between my field bus interface and an Ethernet switch that I have on the floor beneath my demo unit, and then I've connected an Ethernet cable from that to my laptop. I've already set my laptop's Ethernet interface to a fixed IP address. It's set to 192.168.10.200. Remember, last time we configured our fieldbus interface to have an IP address of 192.168.10.100. Those IP addresses are both in the same subnet, so everything should work. I've also registered the Ethernet Master Simulator with the Windows firewall, so the firewall shouldn't attempt to block any traffic from the Ethernet Master Simulator. Hopefully, everything will now work. We should be good to go. Let's do one thing first before we go to the Ethernet Master Simulator and try sending some control words. Let's go to parameter group 0 and bring down process values here and open this up. This will show us what our MOVIMOT is actually doing. We can see the actual speed here in parameter 000. That'll give us some feedback if everything is working correctly. Now, I've got the Ethernet Master Simulator already started here. Let me just pop it up and kind of move it out of the way. I need to, first of all, set the process data exchange word numbers to 5 and 5 and set the RPI to 500 milliseconds. I'm set to the Ethernet IP protocol, and I've got my IP address set to the correct value that my fieldbus interface is set to. So I'm going to click Open Session, and you can see it did successfully connect, and it says SEW Gateway MFE62A. That is good. That's what I want to see. It means it can see the fieldbus interface. I need to change the assembly instances to 150 and 140. That just tells the Ethernet Master Simulator how to communicate. And then finally, I click Start to open up my communications. And we can see that we're communicating. I'm going to uncheck Auto Update PO so that my POs won't transmit the instant I type one in. I'll have to click the Update PO button instead, but that's what I want. All right, so let's go ahead and try to run our MOVIMOT clockwise first. So we're going to put in the control word, PO1. That needs to be 0006. Remember, we're typing in hexadecimal numbers here. Then we have to give our speed, which we calculated. Now the clockwise direction is going to be 104F. So I'll type that in. That should give me my desired speed of 835 RPM. And then finally, I need to put in my ramp value. I'm going to put in 2328, which should give me that 5-second ramp. So let's go ahead and click Update PO and see if our MOVIMOT comes to life and runs at the right speed, and also takes about 5 seconds to get there. Here we go. Now you notice something interesting. Nothing happened. The MOVIMOT didn't spring to life, it didn't start running. We can see by looking over here that our speed is 0, and of course you can see on the camera that it's not turning. You may wonder, why not? Did we do something wrong? And the answer is yes, we forgot to do something. And the reason I did this and allowed it to happen, I wanted to show you this particular problem because this is something that is very easy to forget. And if you do, you will just be absolutely mystified why your MOVIMOT isn't working. Let's go back to Process Data Assignment, Parameter Group 8, Subgroup 7. And you notice that my last parameter, Enable PO Data, is set to No. Whenever you change one of the two configurable parameters, this will always go back to no, and what that does, it tells the MOVIMOT to ignore the process output words. I think this is kind of a safety feature so that it won't do anything unexpected when you make those changes. I need to change this back to yes, and what will happen as soon as I change it back to yes, the drive will come to life. So let's change it to yes, and there we go. You can see it's off and running. Let's go back to Process Values and bring back up the Ethernet Master Simulator here. And there we go. We can see that our speed is 835 RPM. And we can see we're getting some status information coming back in the PIs. I'm going to jot those down because we're going to go back and turn those into binary when we're all done just to see what they told us and if they tell us what we expect. Okay, let's go ahead and stop our drive. What I'm going to do now is change the control word to 0002, and I'm going to give our stop ramp, which is faster, it's 2 seconds. It's 0E10. The speed doesn't matter. We're telling it to stop, so we really don't care what that is. I'm going to click Update PO, and we should see the drive stop in about 2 seconds. Let's see if that happens. All right, yes, I think that definitely worked. It came to a stop in about 2 seconds, and the brakes set at the very end. Let me write down our PIs again. We're going to interpret those to see what they're telling us a little later. And now we're going to run our drive in the counterclockwise direction to make sure it works, and we're also going to see if it takes 5 seconds to accelerate. We didn't notice that when we tested it a minute ago because we were busy worrying about that parameter that was messing us up. So let's change this to a 6 again to tell it to run. We need to change the RPM value to the counterclockwise value. It is EFB1. We're going to change our ramp back to the 5-second ramp. And we're going to click Update PO, and it should take about 5 seconds to come up to speed. Let's see if it does. I'd say that felt like about 5 seconds, and we can see that in fact we are now running counterclockwise. Our value here is negative. That works. So it appears we've gotten successful control of our MOVIMOT over the field bus. Let's bring our drive to a stop now. I'll change this to 2, telling it to stop in the control word, and I'm going to change the stop ramp to 0E10 again for that 2-second stop ramp. I'll click Update PO, and there we go. We came to a stop in about 2 seconds. I think we've had a good success, and that is a great way to wind up our class on a strong note. Let's take a quick look at those PIs to see if they're what we expect, and then I'll have a few final words as we wrap up the class. Let's take a look at those PIs that we jotted down. We'll look at the PIs that we got when the VFD was running. So let's look at PI 1. PI 1 was hexadecimal 0407. We turn it back into binary, it looks like this. Let's look at the significance of the individual bits and see if they match up with what we expect. Bit 0 is output stage enabled. We have a 1 there, which is a true, so we know the output stage was enabled, and that makes sense since the motor was turning. Bit 1 is inverter ready. That is also a 1, so that's true. The MOVIMOT was clearly ready since it was operating. Bit 2 is PO data enabled. That is also true, and of course we know that's true because the VFD was responding to PO commands that we sent it. Bit 5 is the error bit, and it's a 0, which means nothing's wrong. So the final 8 bits is not a fault code, it's a status code. And if we turn this from binary back into decimal, we get a code of 4. I looked this up in the MOVIMOT manual, and that simply means the MOVIMOT's enabled. And that's exactly what we'd expect since it's running. PI2 gives us the speed in RPM. We had hexadecimal 104F. We turn it into binary, it looks like this. But what we really want to do is convert it to decimal. So we feed this into the Windows calculator, and we get 4,175. Now, since this is an RPM and not percentage, we multiply it by 0.2 to convert it to the actual speed in RPM. So if we multiply by 0.2, we get 835 RPM, which is exactly what we asked for. So that looks good too. PI3 is the second status word. It contained a hexadecimal 2E07, which in binary looks like this. As you remember, a number of the bits are identical to the corresponding ones in PI1, specifically these bits right here. They're all showing exactly the same thing, which is what we would expect. However, this bit indicates the status of the brake. If it's a 1, the brake is engaged, but as we can see, it's a 0, which means the brake is released, and since the MOVIMOT is turning the motor, that makes sense. We have a duplicate inverter ready bit, which is confirming, unsurprisingly, that the inverter is ready. Then these 3 bits indicate the state of the 3 digital inputs on the MOVIMOT. And since we have jumpered counterclockwise and clockwise, so we get bidirectional operation in field bus mode, it's not surprising we see 2 1s there. But the F1, F2 input is connected to nothing, so it's showing as 0. And then finally, this last bit here indicates that we're in expert mode. All right, now let's look at the PIs that we got back when we stopped the MOVIMOT. PI1, when we stopped the MOVIMOT, gave us a hexadecimal 0206, which in binary looks like this. The output stage is no longer enabled. That makes sense since the MOVIMOT is stopped. However, the inverter is still ready, and the PO data enabled is still true. We don't have an error here, so that means this is a status code. If we convert it to decimal, it comes out as 2, and the manual tells us that just means the MOVIMOT is not enabled. PI2 sent back as 0. We don't have to do any math on this one because this is the actual speed in RPM, so 0 just means 0 RPM. No surprise since the motor isn't turning. And then finally, our last PI, PI3, contained 2F06, which looks like this in binary. And again, we have those duplicated bits that tell us exactly what the corresponding bits in PI1 told us. But we can see now the brake is engaged since the motor is stopped, so that has changed to 1. The inverter is still ready. Counterclockwise and clockwise are still jumpered to 24 volts, and we're still in expert mode. So, I think that makes sense. We got back what we expected to get back. And that now brings us not only to the end of this session, but to the end of this class. So, we have learned a lot. We've explored MOVIMOT from its simplest operation to its most complex. I just have a few final things to say as we wrap up, and then we'll be done. Just a reminder, if you have any questions about this class, you are more than welcome to contact the training department, whether you work for SCW or not. Simply email us at training@scweurodrive.com. Please do include MOVIMOT D class in the subject line so the email goes to the right person. We will be glad to help you if we can. Just a reminder, however, we are not a technical support department, so the training department can't provide assistance for your specific application needs or to help you troubleshoot. You're going to have to contact your local SCW Eurodrive representative for help with those problems. And with that, we have come to both the end of session 11 and the end of the class. Good job for sticking with it and staying through to the end. Gold star to you. Really good job. I hope you found this class helpful, enjoyable, and useful. And I certainly look forward to seeing you in future trainings. So, have a good day.